The Earth is a trust. This is the final lecture of the class. In this lecture, I'm going to try to reframe some of the big issues we've been looking at all the way along. I'm also going to carry us to the end of the book and to the end of our topics. I hope that you will find these lectures will stick with you. As per usual, you're going to hear me turning pages, and you may also hear a few cat noises in the background. Let's start with the smart grid and the standard model. We have looked at the really interesting instruments and the observations coming from them, particle accelerators and particle colliders. There's one at an important research center in France called CERN, and there's another at the Fermilab in Illinois. Others are located in the other states in the US, also in England and Japan, Switzerland, and Germany. And I have a couple of notes on where you can go look at those if you'd like to know more. Now, I mentioned the standard model, which was developed in the 1970s and refined constantly since then. The standard model names the kinds of subatomic particles, quarks, leptons, bosons, and the Higgs boson particle in the universe, and it describes how they interact with each other. The standard model says that there are four basic forces. First, electromagnetism. Next, the strong force. Then the weak force. And finally, gravity. That's not too hard to remember. Electromagnetism, strong force, weak force, and gravity. And essentially, the standard model can explain everything that happens within and between atoms at the subatomic level. You could say that it captures all of the discipline of chemistry and some of the discipline of physics. One of the basic forces of the universe and physics, gravity, is not well explained by the standard model, and we'll get to that in this lecture. Now, instead of being on a quest to defend the standard model, scientists are gleefully trying to break it apart by designing experiments to test the location and spin of subatomic particles, looking for anomalous data of any sort, trying to see if it's a statistical fluke or a repeatable and unexpected result. They are celebrating problems in the news whenever they find one. Well, what does it matter to you? Most likely, our theories about the atom will direct the kinds of energy we try to harness and also shape our ideas about the kinds of computing power that we can develop. So that's something to keep in mind. To move to a different topic, food ought not to be scarce, but there are plenty of places where it is scarce. It also ought not to contribute to global warming, but the kinds of food that we do eat do contribute. So a place like AeroFarms in New Jersey is attempting to address these issues. Is access to food and water, light and clean air a human right? We would probably say that it is a humanitarian duty to provide these things to anyone who needs them. But would we build a political system around those ideas? This is your world to run, so it's worth thinking about. And to repeat one more point from last week, one of the most practical outcomes of rocketry and spaceflight has been the addition of satellites to our information and control systems. The Roman Emperor Hadrian built an 80-mile wall across the narrowest part of England in 122 BC to control Britain and to give his soldiers something to do. To entertain myself, in 2013, I took a week and walked the wall. The tour company gave me a map, but primarily I used my phone and GPS to check my location every day. I thought quite a lot about technology, the technology that Hadrian used, and the technology that I was using as I passed by farms and over streams and along the ruins of Roman forts and guardhouses. Controlling the world with a wall, controlling the world with satellites. There was a lot to think about. Our last four topics are gene mapping, the age of the universe, computing, and climate change. Let's start with the DNA double helix. The discovery was announced by Watson and Crick in 1953 in England, but we can begin with Gregor Mendel's P experiments in 1854 in Silesia. Mendel was a scholar, administrator, and experimenter who had studied biology and who undertook a series of trials over 8 years to determine what happened to the offspring of self-pollinating and cross-pollinating pea plants. He worked out that there were pairs of genes involved in inheritance, that traits are inherited independently from each other, that some characteristics were dominant, almost always inherited, and some were recessive, inherited more rarely. His results, published in 1865, were rediscovered in 1990 and slowly brought into the mainstream of biological understanding. By the time the 1940s were wrapping up, the question was, Where is heritability located? It isn't located in cell molecules, but should researchers focus on cell proteins or acids? The hunt for the shape of and the structure of DNA required joint work across chemistry, physics, and biology. It also illustrated the same debates over primacy that we saw with oxygen: primacy of data versus primacy of understanding versus primacy of publication. And the solution that the American biologist and James Watson and the English physicist James Francis Crick came up with came at the end of a lot of research. They met at Cambridge, and they were by no means the first to work on the problem. A host of other researchers had narrowed down the area of investigation to deoxyribonucleic acid and identified the nucleotides adenine, thymosin, cytosine, and guanine. Watson was a younger graduate student who had finished his PhD by 23. Crick's studies had been delayed by World War II, so he was an older graduate student at 35, and he was employed at Cambridge's Cavendish Laboratory. Now, they both saw the race unfolding in science. Who will figure out this DNA puzzle first? And they wanted to be the ones. They worked together on the problem. Crick's background in physics was essential for the math that went into the distances between molecules and the angles of the bonds, both of which dictated how the model had to be built. Now, the most complicated moment of the discovery is the use of photo 51. And photo 51 is pictured here on the left. The photo shows the X-ray diffraction results of DNA, and a schematic of the process is pictured there on the lower right. Graduate student Raymond Gosling took the photo for researcher Rosalind Franklin in 1953. She worked at King's College in London, and her colleague Maurice Wilkins gave the photo to Watson and Crick without asking Franklin. They then developed the idea of a helical structure of DNA. Now, the American biochemist Linus Pauling was working on the same problem and thinking along the same lines, but he predicted the wrong shape. Crick, Watson, and Wilkins were awarded the Nobel Prize in 1962, but Franklin had already died in 1958. Process and personality to some degree dictates reality. Rosalind Franklin was assigned to a lab in King's that didn't give her the financial support or research independence she expected to get. Moreover, the work she did using X-ray crystallography was finicky. It was quite hard to crystallize the sample in order to get anything to shoot X-rays through, and she had a knack for doing that. But she didn't necessarily have the willingness to immediately name and claim the evidence within the photograph she herself obtained. Others did see what they were looking for. So she didn't get the credit, and then, worse yet, she died before she could get the recognition she deserved. Just as the discovery and rediscovery of the atom gets told as a standard science is changing story, this is a story of women in science who got cheated. But it's also a story of discovery, and the X-ray crystallography process continues to be the best way we have to examine complex molecules. And you can pause the video, and in the notes you can take a look at a link to a really nice overview of how this is done by the Royal Institute. One of the more interesting outcomes of this DNA double helix is the pursuit of gene mapping. Who are my ancestors? Previously, the only method to answer questions of this sort was historical text and artifact-based research. My grandmother, who was very interested in genealogy, traced my family through county records, visiting graveyards to get dates from gravestones, family Bibles, census records, and artifacts. So what are the kinds of problems to be solved in this research? Well, maybe someone transposed numbers in a date. Maybe two siblings have the same name, and which one of them was it that came to America? Or someone remarried and the family name changed, or someone spilled coffee on a list of names. I have in my possession the list I spilled coffee on, as well as a leather-wrapped kosh, which is a small nightstick capable of knocking someone out, that belonged to my great-great-great-great-grandfather, Thomas Patrick Harkin. He's highlighted there. He was an Irish policeman, and his father came from Ireland. I wondered if he had ever used it, and what kind of guy was he, so just for fun, I sent a copy of that information to a colleague of mine who's doing research on the coal and iron police in the 19th century. I thought he'd be interested in the little weapon. To my great surprise, within 20 minutes, he sent me 4 newspaper articles from Vineland, New Jersey, where my great-grandfather Thomas Harkins served, and it gave an accounts of some of the arrests he made. So it looks like he did actually use his Kosh. But there's one more point to make here. Police work inspired the science of identity. About that time that my great-great-great-grandfather was serving on the police force, French police officer Alphonse Bertillon was developing a system using photos. Photos were paired with standard body measurements in order to permanently record criminals so as to catch repeat offenders. That system was in play until fingerprinting was developed, and fingerprinting was more or less replaced by DNA as an identifying mark. Methods for identifying DNA in labs has been driven by criminal justice and legal needs, like the paternity report you see below. When you send a swab from your cheek to a lab, the DNA is extracted and short tandem repeats are identified. Now, mostly, proteins must work as expected and cannot vary without causing genetic disease. However, and I'm quoting here from the National Institute of Justice, a website that's part of the U.S. Department of Justice, useful differences in DNA must be found in the remaining 0.1 to 1%, which is not known to code for anything specific. Because this section of DNA's precise sequence is not so important, it is quite variable, which makes it possible to use DNA to distinguish between individuals. So this part of your DNA is like your fingerprint. And not only can you be identified, but you can be put into a group of people who share your traits. Using gene mapping, the question, where do I come from and what were my ancestors like, can be answered quite differently. The person who doesn't have the determination to troll through records in graveyards, who doesn't have family records or documents, or a colleague who happens to be a whiz with online research and doesn't have a criminal record, can use basic biological testing to look at their DNA and find out where their ancestors came from and what genetic mix they have within them. By looking at many samples of DNA, we can begin to form a map of people with genetic similarities. Haplogroups is the way we describe this migration. Everyone in a haplogroup can be traced back to a single ancestor. How do we trace ancestors? There are 3 ways: through your mother's DNA, through your father's DNA, and through group DNA characteristics. Maternal DNA is passed through what we call mitochondrial DNA. It sits outside of those 22 chromosomes and doesn't change when DNA is passed down and recombined in children. It just gets handed down. So it shows who your great-great-great and keep going great-grandmother was. The Y DNA is passed down father to son through the Y chromosome with very little change, so sons can use this 23rd Y chromosome to see migrations of their fathers. Daughters would need to get a brother or a father to take this test. Autosomal DNA shows group characteristics. Autosomal DNA are one of the 22 numbered chromosomes excluding the 23rd chromosome, the chromosome that determines sex. There are spots within these 22 chromosomes that are known to vary. These spots are called SNPs, or single nucleotide polymorphisms. You'll get one of those variation spots from your ancestors, so we can use SNPs to find your ancestors. The letters and numbers on this chart are haplogroups that have migrated mostly from Africa outward using paternal migration. At the same time as we are chasing down DNA and putting ourselves into groups within my lifetime and yours, race, which was a standard way of shaping political policy, has become an extremely vexed concept that both sociologists and biologists tells us is a construct and not a scientific reality, meaning that yes, some characteristics are inherited, but that race as a genetic way of describing 2 fundamentally different groups is not a biologically meaningful word. We are more alike than different. And people are becoming increasingly resistant to identifying themselves as a race on census data. So what do we do with those 2 trends? Identify yourself, don't identify yourself, within society and science? That's an interesting question. Gene mapping is also being used to decide where problems are and whether or not to fix those problems and what sort of problem is a problem. This is a whole other set of questions. Who has rights? Will we use genetic markers to redefine someone as not human and therefore not possessing of rights? In 2004, Denmark became one of the first countries in the world to offer prenatal Down syndrome screening to every pregnant woman, regardless of age or other risk factors. Nearly all expecting mothers chose to take the test. Of those who got a Down syndrome diagnosis, more than 95% chose to abort. In 2019, only 18 were born in the entire country. About 6,000 children with Down syndrome are born in the U.S. every year. On the right is my beautiful nephew. For some of this question of genetic rights is simply an ethical case study, but for others it's a question about the people we know. Gene mapping is another question like food, water, and clean air that's worth you developing an informed opinion about because it affects all of us. In our immediate future, CRISPR genetic therapy, adapting, cutting, and repairing genes, is developing at incredible speed. Among the most recent developments is the attempt to cure sickle cell disease. Here, for instance, is a company in the field. What we decide to fix and why is going to depend on our definition of human and human rights. I love this picture of Penny Patterson talking to Coco the gorilla and holding one of Coco's kittens. As you may know, Penny Patterson worked with Coco for 46 years, and her relationship with Coco was among the longest-running experiments in animal learning. Coco learned to use more than 1,000 signs. She joked. She lied. She loved kittens. She made the news in 1978 for her early advances in signing and self-knowledge, and she made the news again in 1985 when she was featured with her pet kitten. Scientists didn't really know what to make of her. Was this in fact science, or was it a relationship that traveled beyond an experiment that could be repeated and verified? Like the question of the atom, the question of where we are and who we are in relationship to the world and to each other is a very old one. Who we are fundamentally is raised by the songwriter David, who lived around 1000 BCE. The passage in the Bible reads as follows: "When I consider your heavens, the works of your fingers, the moon and the stars which you have set in place, what is mankind that you are mindful of them? Human beings, that you care for them. You have made them a little lower than the angels and crowned them with glory and honor. You made them rulers over the works of your hands. You put everything under their feet, all flocks and herds, the animals in the wild, the birds in the sky and the fish in the sea, all that swim the paths of the seas." Now possibly you have heard this passage being referenced by Shakespeare's play Hamlet, when he says in Act 2, Scene 2, "What a piece of work is a man! How noble in reason, how infinite in faculty! In form and moving, how express and admirable! In action, how like an angel! In apprehension, how like a god! The beauty of the world, the paragon of animals, and yet, to me, what is this quintessence of dust?" Shakespeare's work were published in 1623, so that's about 1500 years after the composition of the Psalms. In more recent years, we can consider the words of Viktor Frankl, author of Man's Search for Meaning, and World War II concentration camp survivor. Challenging the meaning of life is the truest expression of the state of being human. In other words, through the medium of art, we have been wondering for a very long time if we are exceptional and how we know that we are. Now, as I said regarding DNA and gene mapping, the question of exceptionalism has morphed into who has rights. It's a subject of fairly intense debate. If you look it up, you will see that chimpanzee labs are being shut down all across the country. And I think this photo captures the tensions of those questions. Are we unique? Who has rights? And I think it captures it exceptionally well. 2 lectures ago, we saw the Victorians tackling our place in the universe through Darwin and biology. Darwin answered this question to some degree by arguing that human beings are descended from simpler life forms, and for us, most immediately, as shared ancestors with apes and chimpanzees. And I had noted for you that he left the existence of the soul, that long-standing entity of poetry and prose and philosophy and religious thought, he left that without a clear answer. But biologists have been attempting some kind of answer for a while. Most of them attack the problem through evolutionary behavioral analysis or through chemistry. To answer the question of why is there something like altruism, why would anyone consider laying down their life for country or God or someone else? To answer that in a behavioral way, some biologists argue that if all of us act as a group, some of us will survive. So they account for the noble anti-survival behavior of the individual by saying that we are, as a species, biologically predisposed to be good to each other and to sacrifice for each other. So if we think of our soul as that aspect of us which believes in something larger than ourselves, we have developed that soul characteristic to survive as a species. Another answer to this question of soul is a chemical neurological approach. The argument is that the sum of the whole is more than the parts, meaning that what we think of as consciousness is something that arises from us having so many neurons and synapses. Our soul is a byproduct of our remarkable brain chemistry. And I've put in the notes a couple of links to something interesting on this subject. Well, if we set aside questions about our fundamental nature and we think about ourselves solely as agents with power, we've managed to wipe out most of the other large predators. The future existence of many species on the planet hangs on the choices that we make. Who has rights has been asked in a form I find particularly compelling: who can suffer? And if we are uniquely accountable for preventing suffering, then asking the question this way moves from a focus on rights to a focus on responsibilities. In any case, believing in God or human exceptionalism, that we are spiritually different in some way from the other animals, is likely to get you in difficulties in the field of biology, unless you are what is called a deep earth ecologist, who sees the whole earth as a living system. If you admit to thinking that there might be a God who created the world around us, you're likely to get the kind of reaction that you would get by bringing a badminton racket to a soccer match. You're just not playing the game, and you're not welcome. By contrast, physics seems to be a little bit more welcoming to at least the wonder and terror of our littleness in a huge universe. One of the best expressions of science impinging on culture is the movie Rebel Without a Cause, the planetarium scene. In this scene, high school kids are taken to a planetarium, and they're trying to be cool, they fool around, they don't pay attention, but at the very end of the show, the end of the universe is displayed, and so lights flash and everybody is pulled to attention, and they blink and they kind of wince, and then the lights go up and everybody kind of shrugs and tries to shrug it off. But there's one kid named Plato, and instead of shrugging it off, he's hidden under a seat, and he's still there at the end of the show, hiding in terror. It's a funny little scene, but it captures a 50s anxiety about what telescopes were revealing about the size and age of the universe. And you can watch that video in the links that I provide in the Blackboard shell. Well, the Big Bang, as it is currently proposed, is a singularity, meaning a place of infinite density. Unlike a black star, our universe exploded out rather than collapsing into itself. And there's no way to do the math for this. Infinity also blows up the math. But I think it's fair to borrow a secondary meaning of singularity and describe a singularity as a start at a single point with no explanation and no known precedents. That's as good a way to explain the Big Bang as any other. Immediately afterwards, there was a period of inflation and then rapid expansion. And there is math for this part of the model, which we will see in a moment. The best estimate we have on hand says that the universe is 13.8 billion years old. We know from what we can see that the universe seems to be moving away farther and faster than and picking up speed as it goes. But no one quite understands why the universe is doing so. And this is one rather beautiful image of the whole thing: soup to nuts to napkin, nothing to bang to increasing acceleration. And if you want to explore this further, I've put a bunch of links in the notes. What are we using to look at space and hypothesize these models? Among the tools are the Hubble Space Telescope and the just-retired infrared Spitzer Space Telescope, and transformatively the new Webb Telescope. They produce, with some help, stunning images like these. And what do these images tell us that confirms or challenges our understanding of the age of the universe? Einstein's theory of general relativity helps us with the understanding of the size and the age of the universe. He said that gravity and mass interact with space and time and light. The gravity, or mass, of a star or a planet will warp the space around it and slow down time alongside of it. Light will stretch along that warped space, and light will shift colors as it warps and stretches. The shift is called the cosmological redshift. How much red we see shows us how far away other galaxies are. The red and the blue in the image on the left shows you the relative distance of those stars, the red being farther away. These images tell us both how far light traveled and how long it took for the light to get to us. So that redshift indicates both distance and age. When we try to think about space and dark energy and what matter exists in the whole universe, there are two camps that do this kind of thinking. One is called experimental physicists, and the other is called theoretical physicists. Theoretical physicists like Albert Einstein and Stephen Hawking relied on mathematical models and primarily worked with a few colleagues in the field. The experimentalists were people like Galileo or Enrico Fermi or Rosalind Franklin or Ben Franklin even. They needed and required funding for their tools. Today, anyone who would direct an experiment using colliders, telescopes, radar detection arrays to measure energy, energy waves, pulsars, and black holes, all of these are experimentalists. And these items are generally incredibly expensive, and they're owned or promoted by governments who do want a practical return to these experimental investments. Of course, there are things that we are still trying to explain that do not have a practical application, but typically, when we invest in big stuff, we want some kind of return. But there's one thing that we're still trying to figure out, and that is, we really think that the energy we can measure doesn't account for all of the space and energy that there is. Dark energy is what we call the thing that fills the rest of the universe. Does dark energy have a mass we can detect? It seems to surround and hold everything else that is detectable. If we can find out what it is, what will we do with that knowledge? Either way, whether practical or theoretical, we desire a unified theory to explain our world and the things in it. In some writing, this unified theory is called quantum gravity. But for the moment, everyone agrees the paradigm is open. We're still looking. This graphic comes from a history hit show that I watched recently, and I thought this particular image was rather nice. It shows the very short time that we have lived in what we would call the present. And personally, looking back down that pathway, not of the Big Bang, but of our short human history, I'm willing to accept that another idea about how atoms work, or about the age of the universe, or about the nature of time, may come along. For me, the lesson of history is to stay curious, to work on your math skills, and to stay open to new organizing ideas. We're shifting topics now to something we encounter not as philosophy, but as an everyday experience, computers. The story of computers runs back quite a long way, and 4 precursors to consider are these: the abacus, supporting mathematics and commerce; the Antikythera mechanism, an early computer of planetary and calendrical cycles; animatrons, motion machines that imitate humans and replicate work or art; and then Leibniz's stepped reckoner, calculating machines that take mathematical functions to the next level. The revolution in computers and the internet is something that crossed the lives of most Gen Xers. I encountered my first computer in high school and got my own first computer in college as a senior. It had no operating system of its own, but it was extremely rugged. I took that computer to China and it served me very well, but it was connected to nothing. In fact, while I lived there, I had to bicycle 20 minutes to get to an international phone. I used the internet and a workplace-provided computer first as a graduate student in 1990 at Lehigh University. And I remember when cell phones became a possibility and then when they were hooked into the internet. So there is, across my own career in life, a radical change in information and communication. The story has a few famous names. For computer and computer design, Steve Jobs and Bill Gates. For the internet itself, there is the U.S. government's determination to be decentralized and the person who established the exchange protocols, Tim Berners-Lee. Corporations are as important as the U.S. government: IBM, Google, Facebook, Apple, and Microsoft. Information affiliates, commercial platforms, have weighed in heavy: Amazon and Alibaba. And I'm not even bringing in photography and the telegraph, although to do the story justice, I should. I have a couple of links for you to look at in the notes. The story of computers usually starts with Charles Babbage's difference and analytical engines and Ada Lovelace's algorithms. Babbage was a British mathematician who was independently wealthy. Among other things, he worked on problems like standardizing astronomical tables for the Cambridge Astronomical Society and tables of logarithms to help sailors find their way in navigation. These tables were calculated by hand, and they frequently had errors. Babbage's idea was to calculate by machine and so avoid human error. He petitioned the British government, but like many organizations, they declined to fund what they didn't really see the use of. The sketch on the left became the machine you see on the right, funded and built in 2002, not by the British government, but by the Science Museum in London. It took them 17 years to do it, and it works. Ada Lovelace was a friend of Babbage's. She was the daughter of the British poet and revolutionary Lord Byron. Her mother made her learn math in order to keep clear of possible inherited tendencies to insanity. That's one way to do it. She wrote up instructions for the machine, an algorithm that it could carry out. Now, what I'd like to remind you of is that computing is both theory and drudgery. It's figuring out what formulas will answer questions, what machines can help you to run those formulas, and who can you persuade to either do the calculations or build the machines. This is ENIAC, or the Electronic Numerical Integrator and Computer, built at 1945 at the University of Pennsylvania for the Army and meant to help with calculating ballistics trajectories for weapons. Curiously enough, or maybe not so curiously enough, some of Babbage's work was in the same area, meaning computing and weapons are linked. ENIAC is described as Turing complete, meaning it is able to solve different kinds of problems through reprogramming. Another way to describe Turing complete is to say that it can handle if-then statements and it can store information. ENIAC had, as part of its calculating machinery, 20,000 vacuum tubes. The previous way to calculate is to do the work by hand, and rather than being illustrative or decorative, as they are in this photo, women were, as we know, essential to computation. From the Harvard College Observatory, which we talked about a few weeks ago, right through the NASA's Langley Research Center, which I mentioned last week, women were calculators of indispensable information about the stars. I'd like to draw your attention to semiconductor transistors. From the Apple IIe that my mother purchased and loved, to the phone that you have in your hand, all of them work on semiconductors. To quote my student Larry Graver, transistors are why computers have evolved from the expensive, bulky, power-draining, massive machines to small, cost-efficient, fast, portable devices. Transistors are why many devices are made possible: intelligent cars and buildings, PCs, cell phones, iPods, and PDAs, just to name a few. The transistor is the most common machine in the world. You can light a fire, possibly take down a deer with a crossbow. You can put up a tent, cook a can of beans, and hand-stitch a face mask using your own steam with just a few simple devices. But for everything else, you'll probably use a transistor-filled computing device. The future of ubiquitous information is the future of ownership, privacy, rights, and work. It would be fair to say that the developments of biology, what you can know about your genes, intersects with the developments of information technology. It gets cheaper and cheaper to own and manipulate the data essential to yourself. Who has the rights to your personal data? This is a question being fought over now and will continue to be a fight into your future. The ability to mark anything once, irreducibly, is one of the things that blockchain as a feature of computing can do. It created a market for digital art. And the outcomes don't have to be all that serious or earth-shattering, although they can be surprising. The image above, Nyan Cat, or the flying Pop-Tart cat, having been authenticated as a one-of-a-kind image by blockchain, sold for almost $600,000. Well, our most recent challenge is machine learning, or AI. AI is a tool with breathtaking applications, and it is evidently growing by leaps and bounds. AI is built on pattern detection algorithms that make predictions using very, very large batches of data. In essence, AI scrapes the internet for answers to your questions and produces results that are roughly right. The learning tool is not bounded by what it already has learned, it's bounded by what it can access. It is sometimes wildly wrong, but AI can be helpful with the right application. And I've put in a few useful notes in the links in the notes for you to explore a little bit further on AI. Our last topic is climate change. This is the first and in some ways the most memorable image I ever saw regarding climate change. It's maybe 20 years old now, but it really stuck with me. It scared me. as I hadn't been scared by anything before. It suggested that large things, things beyond our control, were happening. There's a recent article, which I put in the notes, that brings things up close. The planet has warmed more than 2 degrees as heat-trapping gas accumulates in the atmosphere, and you can read that in the notes that I've linked to the Washington Post. And this page is something I ran across recently that also rattled me. It was the EPA webpage maintained by scientists who disagreed with the previous administration's take on climate change and science. It's not surprising that politicians and scientists might disagree about what to measure and how and why, but it was disturbing to see it highlighted in that way. The carrying capacity of the Earth isn't known. Some scientists have pegged it at 9 billion people. It's hard to say, given what we don't know about how pollution can be mitigated and if food production will be able to reach the people who need it. We also don't know how much we will have to do or to change in order to reposition where we live and how we live, but this chart is an interesting speculation on that topic. A trust is something you put into place for the future. I think the history of science should lead us to think hard about what we want to put in place and hold in trust for the future. And this image is a glimpse of the young Dutch engineer Boyan Slat on his first attempt to clean up the Great Pacific Garbage Patch. I think it's a cheerful note to end on. We are still voyaging out to solve problems with the best tools that we have.